Hello, I'm Dylan Herron, and my project is GPU ray tracing for realistic scenes. The goal of my project is to create more realistic scenes than is typically possible with rasterization methods. The image you see here is the final result, but there was a lot of work to get this far. The first step is to generate the trivial ray tracer. This is done by performing a ray triangle intersection test on all the triangles within the scene for each ray. Initially, there is only one ray per pixel in the scene. Because there's only one ray per pixel, there cannot be any form of reflection, shadows, or refractions, thus making the scene look pretty unrealistic. But it was a necessary step to get all the calculations done without actually having to worry about the complexity of having everything else added, such as the reflections. In order to get the triangle list to the GPU fragment shader, I stored a list of vertices as well as normals and material identifications for each of the triangles in a texture, which can be accessed relatively quick on the GPU. Something interesting to note is that even with all the math that's involved in the later steps, the slowest part is by far reading out stuff from memory. To keep things focused on using the principles from this class, I opted to only use procedurally generated textures. In other words, there's no rasterization in any of the screenshots you will see aside from the rasterization of the Perlin noise that I pass in to generate the procedural textures. The next step is to add reflections. This adds quite a bit of depth to the scene already and probably is one of the quickest ways to get the scene to look relatively good. Bearing in mind that if you set the max ray depths to something small that's like less than 5, the scene can still render in like 10 frames a second. In addition, you can also see that shadows were added to the scene. One thing that comes up a lot with shadows is aliasing, but I found that I could get rid of like 90% of the aliasing if I just offset the normal, the intersection and the direction of the normal by some small amount. The next step would be to add refraction, as you can see in this image here. Something to notice is how the light bends as it enters the cup. Refraction in this program actually follows Snell's law, which states that light rays change direction when they enter materials of different indices of refraction. Additionally, the number of rays is now exponential. Because you can either have a reflection ray or a refraction ray, and how I blend them depends on the ray type and the material. Having completed the first pass of shadows, I noticed that there's something very wrong about some shadows. For example, not all shadows are the same. On my first pass, I did not take into account that the possibility of shadows being caused by glass surfaces. To make the scene look realistic, I had several options. I could simply check if the target point was being shadowed by a glass surface and apply a constant half shadow to that. The issue with this approach is that not all glass is the same and light does not always enter glass the same way. So alternatively, I could render the scene from the view of the camera and apply shadows that way like we did in class. But this is a rasterization technique which either renders a lot of unneeded stuff in a very massive texture or has a very limited quality of final image. The last option was to solve some very computationally complex systems of equations to find exactly how light traverses through the transparent objects. Realistically, to generate shadows, you need to start from the light and ray trace to the target. Unfortunately, it's very complex to solve an equation just given the start point, the light, the end point, and which is the target, and a list of triangles with interpolated normals. Keep in mind, it's not even trivial for the simple case where we assume just a single bounce of light. This kind of algorithm might work well for ambient light sources, but I just couldn't find a way to get it to work real well with shadows that need to be real crisp. So in order to get the best performance while kind of faking making it look kind of realistic, I decided to go ahead and fake the shadows under a few assumptions. So when light bends, as it bends, it actually scatters out. That's the first assumption. And then when light scatters, its intensity decreases. Thus, if light bends a lot, the intensity of the light decreases a lot. So the diagram here shows how this applies to the ray tracing problem. The red ray is the direction that most of the light goes through in each of these diagrams, and the blue ray is the ray, the straight line fake ray that I'm simulating. So in the one on the left, you can see that the ray that's coming in, or the true ray and the fake ray, are pointing in the same direction. So the estimation is 100% correct there. However, in the one on the right, you can see that the true ray actually bends out in a way from where the simulated ray goes. So I just need to detect the difference between where the simulated ray goes and the true ray goes. And if I can get some idea of how the dot product between those looks, I can adjust the final intensity to be less if the true ray is not in the same direction as the estimated ray. Another thing to keep in mind when doing shadows of transparent objects is the longer you're inside of a transparent object, the less light is capable of leaving that object. So I made the intensity of the light that traverses through the object decrease with distance. That's pretty simple. Another thing that's kind of important is getting the right color of the transparent object that the light is passing through. So not all transparent objects are clear. Sometimes you have red and blue, like the liquid showing here. So I just blend the light as it goes through those objects to make things look a little bit more realistic. Now that I've got all that stuff done, I decided I might, try it on something a little bit more interesting, such as water. So as you can see in this scene here, there's a little bit of water on the far wall. Notice how the light bends as it hits the water. You can tell that because of the reflections kind of bend, and as also the refractions. It's a little bit hard to see, but the refractions do also bend. I decided to add another light to the scene that's directly over the water to show the ability for the water to have shadows. The surface of water doesn't technically have shadows, it just has locations where light is kind of converges and diverges because of the surface of the water. But programmatically, to get this effect, it's essentially the same as the estimations I used for shadows before this, except for now I'm using it on a sine wave instead of just a surface. This effect is a little bit hard to see when you're just standing out, so I did a side by side. As you can see on the one on the left, or hopefully you can see depending on the color contrast, there's no shadows in the one on the right. Also, it does have these little shadows that adds a little bit to the scene. Something else interesting to note is that the light is not actually a cone light. This is a point light, and the cone effect is coming just from the shadows of the light object. The light object has a small region of glass midway up, as you can see, and that's just as a demonstration of how glass can affect the shadow color again. The last thing I attempted was to make things that were out of focus look blurry. Now this was a really hard effect to actually get, because it was the only effect so far that it required anti-aliasing. Everything else didn't really require anti-aliasing. And anti-aliasing is very expensive computationally. To show this effect, on the far left there's the blur without any anti-aliasing, a little bit in the center, and then the most that I tried for anti-aliasing on the right. And even that doesn't look too good, and that took orders of magnitude longer to generate that screenshot than any of the other screenshots in the previous pages. Even though it wasn't entirely successful, I thought it might be worthwhile to mention how I did this, or tried to do it at least. The ideal ray, that is the ray that comes from a pinhole camera, is shown in black. The estimated ray here is shown in blue and intersects the ideal ray at a distance away, at a focal distance away from the camera. with some epsilon separating out the ideal ray and the rendered ray. So that's my project. Thanks for watching.